I welcome all the students present in this video lecture. In today's lecture, we are going to discuss about the buoyancies and metacentric height. We focus on analytical method to calculate the metacentric height, and these derivations of metacentric height calculations is repeatedly asked in our university examinations. So before starting the today's session, we just start with the what is buoyancy. For buoyancy, let me take one tank and I have filled this tank with the water. And if I have one another object and I put that object in this tank, then the it displays the some amount of the fluid. So suppose let's say this is a fluid that is displaced by this object, as I have partially immersed this object in the fluid. This object is displays this weight, and the weight of the fluid that displays is also generating the forces on the opposition directions of this weight of an object. So this force is called as a buoyancy forces. So for the buoyancy effect, the Archimedes principle is very important. So as per the Archimedes principle, whenever a body is immersed wholly or partially in a fluid, then it is lifted by a force equal to the weight of the fluid displaced by the body. Means here we have one object, and this object is immersed partially in this fluid, so it displaces the certain amount of volume, and that weight of the fluid displaced by the object, it is same as the weight of this object. Means the weight of the object which is immersed in the fluid equals to the weight of fluid displaced by the object. So let's say here I'm taking one object having a width of b and the height is a capital H, and I immerse this object in the fluid for only the height of this H, not for the whole height. So it is a partially balanced. So the fluid displaced by this object is the volume of this object. So the volume of this object is b into small h into the length, that is a perpendicular dimension to this plane of projections. When you insert any object in the fluid, it displaces the fluid equal to the weight of object that you have immersed, and it also creates an upward forces which is equals to the weight of the fluid displaced, and that force is called as a buoyancy forces, and which is acting in the opposite direction, means in the upward directions, and weight is acting in the downward directions. So that force is called as a buoyancy forces. Now for the particular this example, if we want to calculate the buoyancy forces, then the FB means the buoyancy force equals to the weight of water displaced by the body. Here I'm taking the fluid as a water, and this body is having a dimensions of capital B into H, but I immerse this object at a height of small h. So the weight of water is m into g, that is a buoyancy forces, and we know that the m equals to rho into g into v. So we get the rho gv. So rho gv, rho is density of water, g is a gravitational constant, and volume of a body displaced. So here the volume of body which is immersed in the fluid, that is b into small h into the L, where these buoyancy forces are acting. So the buoyancy forces are acting at the center of gravity of this volume displaced by the object. It means suppose the if I'm taking this object, so at this point this g is located, that is a cg of this object, but the volume displaced by the object, it is like this. So here I have this center of gravity for the volume displaced by the object, and at that point these buoyancy forces are acting. So this is the called as a b, that is a point of buoyancy, and this is called as a g. So buoyancy forces are acting at this b point, and the weight or the gravitational force are acting on the cg. So now we are going for the metacentric. It is defined as a point with respect to which the body oscillate in a liquid when body is tilted through a small angle. It is only applicable for the partially immersed body, means a floating body. Suppose this is a floating body, and this is the neutral axis that I have indicated using this green pen. And when I give a certain small angular displacement to this floating body, let's say I am applying some forces over here, so body is moving in these directions, and then again it is come back in this position. So neutral axis, suppose in this position it is say like this, in the vertical positions it has a certain like this, in suppose I'm giving the anti-clockwise, then it is moving over here. So at one point the all the neutral axes are intersecting for the different positions, and this point on which around which this floating body is oscillating, so that point is known as the metacenter. In this example, in this figure, I'm going to explain you this G is a center of gravity at which the weight of body is acting, B is the buoyancy forces, and now suppose I'm giving this inclinations to this, so in neutral axis the G and B point is that, and for the original positions I have this B1. So for the stable positions or for the vertical positions, I have indicated the buoyancy force at is B1, and here it is B. So the both the neutral axes are intersecting at this point, that is called as it is indicated by yellow line, and this is called as a M, and the name of this M is called as a metacenter. So this is called as a metacenters, and metacentric height is a distance between the center of gravity and the metacenters. So student, here there is a three different points are there. One is called as a M, and the name of M is a metacenter, G that is a center of gravity, and B that is a center of buoyancy. So the distance between the center of gravity and the metacenter is called as a metacentric height. So this is the concept of metacenter, and metacenter is applicable when your object is only the floating, means it is a partially immersed in the fluid. So we start with the derivation, analytical method to find metacentric height. So I'm taking first one object. Suppose this is my surface, free surface. This is indicated by AB. I have water or any fluid, and I take the one object which is floating in this fluid. So let's take this point, it is the G point where the W weight is acting. This is the point B where the buoyancy forces are acting. And if I'm taking the projection of this object perpendicular to this plane, this is the same width B is there, and the length of object is the L. Now I'm considering one small strip over here. This is the strip that I consider at a distance of x from the neutral axis, and having a width is dx. Suppose I'm plotting over here. So this is the surface AB. This is the object at first position. This is the neutral axis. When it is having some angular displacement, suppose let's say this is the metacenter M. So one line is passing through this metacenter. This angle between these two neutral axes is a theta, and the new positions of this object is, let's say this is the B, and here it is B dash, this is A dash, and this is A. Let's say this is the original axis O, so B is moving over here and A is moving. Suppose this is the A dash and it is B dash, and our neutral axis is looks like this. So the angular displacement of this object is becomes a theta over here, and it is a theta. So suppose I enlarge this figure of one end, then it is O point, then this is the B dash point, and this over here it is the B point. So this is the angular displacement we have given, that is a theta. So now the strip which we have considered over here, the same strip we can consider over here. This strip is having a thickness of dx, and the distance of the strip from the O, that is at x. So here it is O, here it is the x is the distance, and this is, I want to calculate the width or the length of the strip. Then we have the arc length equals to the radius into the angle. So here the length of this strip is, the radius is x and the angle is theta. So we have x into theta, which is equals to the length of this strip. First we calculate the area of the strip. So here it is like this, we have the strips. So this width is a dx, and the length of the strip we get x into theta. So area is length into the width. So we get x into theta into dx. Now if I want to calculate the volume of the strip, then area into length. So it is x into theta into dx into the length of the strip we consider throughout the length. So we need to multiply it with this L. So here it is L. That is the volume of the strip. Here in first position we have this object in ABCD positions. In second it is A dash, B dash, C dash, D dash. So due to this gain over here, this volume is displaced, and due to this angular displacement, the volume which is occupied this OBB dash, the same volume is displaced of the fluid, and due to that there is a gain in the buoyancy forces. So gain of the buoyancy force due to the right hand side or the displacement of an elementary streams indicated by small value is there. So dfb is there, and buoyancy force is equals to rho into v into the g. So density of fluid is that, volume of the strip is x theta l into dx, and g is a constant. So this is the forces, buoyancy forces gain in the OBB dash. Similarly, this is the right side, and we have another triangle like this is the OA, and we have this OA dash. So same one strip is also there. So we also get the gain in the buoyancy forces over here in these strips on the left hand sides. So similarly we have this gain in the buoyancy forces in the strip considered in the OOA dash. So we get the same value of the buoyancy forces, that dfb equals to rho g x theta l into dx. Now students, suppose I'm taking this is the axis of AB and this is AB dash like this. So here it is O point, this is the A dash, this is the B dash, or it is B, and here it is A. So one strip is there, another strip is acting over here. So one buoyancy force is there which is acting in the downward directions, here it is acting in the upward directions. The perpendicular distance from this O is x over there, in this side it is also x. So it creates the couple, like suppose I'm representing this O point, x distance, one is acting in the upward directions, another is acting in the downward directions, and the intensity of F, that is a force, is there. So the couple is having a moment that the F or the force into the 2x. So this is the moment of couple generated over here. So now these two elementary buoyancy force acting in opposite directions and produce an anti-clockwise couple. So the moment of the couple, that is dfb into x plus x means a 2x. So we get the rho g x theta l dx into 2x. That is the moment of the couple of the strips. So if we want to calculate the total moment, then we need to do the integrations of this. So it is a 2 rho g theta l into x square into dx. Now this couple, due to this DFB means the buoyancy forces is tried to rotate this model or ship or any object in anti-clockwise directions, and it must be balanced by the weight that is displaced. Students, let me first explain you. In this position, suppose we say, and second position is like this. In the first position, the buoyancy force is acting at this B1, which is over here. In second point, suppose B is there, so it is acting. So this moment of the buoyancy force is equals to the buoyancy force moment generated due to this displacement in the center of buoyancy. So this moment will be compensate with the moment that is created by FB into BB1. So the moment of this displacement is caused due to the moment in the center of buoyancies, means the couple generated which rotates this object in the anti-clockwise directions is generated because the center of buoyancies are moved from B1 to B. So it is balanced by this moment. So this moment is FB into BB1. So here we get this is a clockwise moment, or it is a cause. We can write as a cause by the displacement of center of buoyancy. So we get finally our expression that FB into BB1 equals to the integration 2 rho g theta L x square into dx. Integration 2 rho g theta L x square dx equals to FB into BB1. We have this diagram over here, that this is the B1, this is the metacenter, and the new position of center of buoyancy is B1. So we have this, and this angle is a theta. So we consider the sine theta in this triangle B1M. So we get sine theta equals to BB1 upon the BM. So if we make subject BB1 from this expression, then we get BM into sine theta. So we put down this expression over here. We get FB into BM into sine theta. Now we know that FB equals to the W, that is a weight displaced. So the W into B into M into the sine theta equals to integration 2 rho g theta L x square into dx. For the small angle, we can consider the sine theta equals to theta equals to tan theta. So we cancel out the theta and sine theta over here, and we also know that the L into dx is the area of a strip. So we put it down the value of this two over here. So we get W into BM equals to the integration 2 rho g into this x square. L into dx is the having a value of dA, so we get this dA. Rho ng is constant, so I kept it out of this integration. So finally we get 2x dA. So here the 2x square dA integration is a moment of inertia of the elementary strings about the y axis, that is a perpendicular to the plane of paper. So we get a W into BM equals to rho g into the moment of inertia, and W is the weight of body. So the weight equals to the rho into g into the volume. So we'll put it down and we make a subject that BM. So BM equals to rho g into I upon rho g into the V. So rho g is cancel it out, and finally for the BM we get that is I by V. Furthermore, if we go for this geometrical discussion, then it is M, here it is the G, here it is the B. So we know that the BM equals to GM plus BG. So now if we put it down the value of BM over here, then the BM is having the value of I by V, and BM equals to, we know that it is the GM plus the BG. So if we make the subject over here, so we get GM plus the BG is having I by V. So finally we get the GM equals to I by V minus BG. So this is our final expression to find it out the metacentric height of an object, where we can write this is GM is the metacentric height. So this is very important expressions for the university examinations as well as for solving the different numericals based on the center of buoyancies and the metacentric height. So thank you students for attending this lecture.